Here I want to cover the actual dynamics and orbital dynamics. Here we introduce Galileo, Newton, and Einstein. Dynamics is a branch of mechanics and ultimately physics, and is concerned with the motion of bodies under the action of forces. Kepler had an inkling that there was some force that kept the planets in orbit, but never was able to develop a comprehensive physical model. That started with Galileo and then Newton. Galileo did experiments that involved rolling balls down and up inclines. When rolled this way, the ball returns to almost the same height as it started. Galileo felt that friction accounted for the difference. Otherwise, the ball would have rolled to the same height. He found that if he changed the angle of the incline, the ball still rolled to the same height. He surmised that a ball rolling on a horizontal surface would never be able to reach the same height as the starting point. He theorized that lacking an external force, it would roll forever. Inertia is the tendency of objects to remain in constant motion. The law of inertia states that an object tends to resist changes in motion. Galileo stated this as a basic physical principle. A body moving will continue in the same direction at a constant speed unless disturbed. The Aristotelian model suggested that a constant force was required to keep an object in motion. It did not take into account forces like friction counteracting forward motion. Objects in motion slow down because of counteracting frictional forces. Otherwise, they'd remain in motion. The ancients always knew that falling objects gained speed, but they didn't have an explanation for it. Galileo studied kinematics, a branch of mechanics that focuses on moving objects. Galileo used a water clock to time balls rolling down gently inclined slopes. He found that the total distance for a given time increment was proportional to the square of the elapsed time. A ball would go 4 times as far in 2 seconds as in 1 second, 9 times as far in 3 seconds as in 1, and so on. This can be written as an equation. P of t equals a constant c times t squared. P of t is a measure of length, t is a measure of time, and it's squared. Here's the same equation with units. The constant c must be in units of length divided by time squared for the equation of P of t equals ct squared to work. When t equals 1, P of 1 is equal to c by itself. C is equal to the distance an object falls in the first unit of time. That's a convenient way to determine c. In the animation, the incline is set to 30 degrees from horizontal. Here are the position measurements along the incline for each second. P of 1 is 2.45. In fact, if we divide any p-value by the corresponding t squared, we get 2.45. P of t is an exponential function. The y component of P of t is the cosine of theta. The cosine of 30 degrees is 0.5 or 1/2, so the y component of c would be 4.91. Galileo noticed that the balls rolled faster when the incline angle was increased. Here theta is 60 degrees. Here are the positions plotted. Note that the exponential curve got steeper. P of 1 is now 4.25, which corresponds to a faster rolling ball. As we said before, every instance of p divided by t squared would equal 4.25. The y component of P of t is now the cosine of 60, which is 0.866. 4.25 divided by 0.866 equals 4.91. This is the same result we got before with the 30-degree inclination. From these results, Galileo could determine the rate of motion in freefall. Freefall is an inclination of 90 degrees. P of 1 would be 4.91, the y component of the previous 2 experiments. That's the c value. That's the value of c. We can plug that into our equation. If we plot that out, here's what the positions would look like. Now every p divided by t squared equals 4.91. This makes sense since the cosine of 90 is 1. Galileo would have had to determine this mathematically. His water clocks weren't responsive enough to measure an object in vertical freefall, even if we were able to throw it off a tall building like the Tower of Pisa. Here's the object in freefall again. Once Galileo knew how position changes with time, he could figure out the velocity of the falling object at any time. He could also know how far it travels in a specific time. Let's start with defining a time interval. We'll determine the position at some time t. The basic equation is P of t equals c times t squared, since the position is proportional to the square of the elapsed time. Now let's calculate the position at some later time t1. The elapsed time interval from t to t1 is simply t1 minus t. The change in position is thus p of t1 minus p of t. Velocity is change in position over change in time. That's the fundamental definition. We don't know the specific velocity at t1, but we can compute the average velocity from t to t1. Let's set t to 0 and t1 to 1. The position at time 0 is 0. The position at 1 second is 4.91. Let's plug in values for the function p. That equates to 4.91 meters per second. Let's do that for t equal 0 and t1 equal to 2. Let's compute the average velocity in the first 2 seconds. That's p of 2 minus p of 0 over 2 minus 0. P of 2 is 19.62. And divided by 2, that equals 9.81 meters per second. The average velocity keeps increasing. This makes sense since the instant the object was dropped, it had 0 velocity, and then it picks up speed. The average goes from 0 to 4.91 to 9.81. The average doesn't account for this variable change in velocity. After 1 second, the average velocity was 4.91, but at the 1 second point, it had to be something greater than that. We'd like to know the velocity at a specific point in time. That implies no time interval. If we make the interval very, very small, or 0, we'd be dividing by 0, which isn't allowed. We'll need an alternate method. This perplexed mathematicians for thousands of years. It was not until calculus that a solution was found. The derivative lies at the heart of calculus. Start with the equation for distance given time, p of t equals c times t squared. Let's then compute p of t plus some delta t, where delta t is greater than 0. We called delta t t1 before, now let's call it delta t. Here's the equation for average velocity between t and delta t. P of t is ct squared. Let's make that substitution. Let's also rearrange the terms in the denominator. The t minus t is going to cancel out, leaving us with delta t. Here's an expansion of t plus delta t squared. Let's then multiply all those terms by c. We have a ct squared and a minus ct squared in the numerator. Those will cancel. We have a delta t in all the terms in the numerator and the denominator. We can take those out. This leaves us with 2ct plus c delta t and no denominator. This is the average velocity over delta t time interval. Now let's figure out a formula for the instantaneous velocity. If we take the limit as delta t approaches 0 of 2ct plus c delta t, the c delta t term goes to 0, and we're left with 2ct. Because of the algebra, we avoided dividing by 0. Calculus tells us the instantaneous velocity at a given time t is 2 times c times t. In calculus, 2ct is the derivative of ct squared. An average over an infinitesimally small interval is the instantaneous velocity. It approaches the exact result. That's why the derivative is a fundamental calculation in calculus. Let's do the same thing for acceleration. Acceleration is the change in velocity over the change in time. Here's the equation for average acceleration between t and delta t. V of t is 2ct. Let's make that substitution. Average acceleration is 2c times t plus delta t minus 2ct over t minus t plus delta t. The t minus t in the denominator is going to cancel out. Let's multiply 2c times t and 2c times delta t. Here we have 2ct and minus 2ct. Those are going to cancel. That reduces the 2c delta t over delta t. There are delta t's in both the numerator and denominator, and those will cancel. We're left with 2c. We could take the limit as delta t approaches 0 like we did before, but there's no delta t term here. That's an unnecessary step. Velocity was changing over time. Acceleration in this example is constant. A of t is 2c. Since we're talking about a constant acceleration due to gravity, we prefer to call that g. From our empirical experiments, we know that c equals 4.91 meters per second squared. G then equals 2 times c, or 2 times 4.91. That equates to 9.81 meters per second squared. This is the acceleration due to gravity. Velocity then would equal g times t. We substituted g for 2c. That's t seconds times 9.81 meters per second squared, which, when you do the reduction, ends up in meters per second, the units for velocity. If g equals 2c, then c equals 1/2 g. We can make that substitution in the equation for position p of t. Position is 1/2 gt squared. All of this works because acceleration is constant. If it were not, these equations would come out differently. Newton devised a notation for derivatives. The derivative of the equation for position is velocity. Newton expressed that this way: p primed of t equals v of t. Likewise, v primed of t equals a of t. The derivative of position is velocity, and the derivative of velocity is acceleration. You can do double derivatives. The double derivative of position is the derivative of velocity, which is acceleration. There's also a dot notation. This is convenient for vectors. P dot equals v, v dot equals a, p double dot equals v dot, which equals a. Gottfried von Leibniz has his own notation for derivatives. In his notation, velocity is the derivative of position expressed as dp dt, and acceleration is the derivative of velocity expressed as dv dt. Newton was credited with inventing calculus. Leibniz actually invented it independently at the same time, and his notation proved to be more useful. This leaves us with three fundamental equations. Acceleration is the derivative of velocity and is equal to g. On Earth, g is 9.81 meters per second squared. It would be different on another planet. Next, velocity is the derivative of position and is g times t. Position is equal to 1/2 g times t squared. And here's what all that looks like animated. The plot of position is an exponential curve that equals 1/2 gt squared and is in units of meters. The velocity increases linearly, equals g times t, and is in units of meters per second. Acceleration is constant and equals g, or 9.81 meters per second squared. The general form of these equations account for initial conditions. Position is the initial position p0 plus initial velocity v0 times time, or t, plus 1/2 gt squared. Velocity is the initial velocity v0 plus g times t. Acceleration on the surface of the Earth is g, which is 9.81 meters per second squared. Galileo, in developing his law of falling bodies, found that all bodies fell with the same constant acceleration of 9.81 meters per second squared. Oddly, gravity had the same effect on all objects regardless of their weight. That wasn't the case for forces applied to objects. If you're applying a force to an object, the heavier they are, the more force has to be applied to move them at the same velocity. Gravity didn't seem to work that way. Galileo wasn't able to create a vacuum. This is a theory he developed. Here's a thought experiment he conceived to prove it. Take a feather and an anvil and tie them together with a string. Now drop them. Assume this is all in a vacuum. If the heavy anvil falls faster, then it's going to pull down on the feather. If the feather falls slower, it's going to pull up on the anvil. The anvil speeds up the feather, and the feather slows down the anvil. The net effect is that the whole apparatus falls slower. However, a feather, string, and anvil weigh more than an anvil and surely more than a feather. If the whole apparatus is heavier, then it all should fall faster. Experiments proved otherwise. Everything falls at the same rate regardless of weight. David R. Scott was on the Apollo 15 mission. On the surface of the moon, he was in a vacuum. Here he drops a hammer and a feather. They both fall at the same rate, proving Galileo's theory. Galileo, in studying kinematics, studied compound motion. Here's an animation that compares downward motion with horizontal motion. The ball on the left falls vertically with no trajectory. There was no initial horizontal impetus, hence no horizontal motion. The vector for the ball falling vertically is a velocity vector. It increases over time. The acceleration vector would have pointed in the same downward direction, and its magnitude would have been constant. The ball on the right has no downward acceleration. An initial impetus gives it a horizontal acceleration, and from there it travels at a constant horizontal velocity. The ball in the middle has both motions, horizontal and vertical. That's what we call compound motion. For the middle ball, the downward vector is acceleration. The green vector is velocity. For the ball in the middle, the downward motion is synchronized with the ball in vertical free fall. The horizontal motion is synchronized with the ball with constant horizontal velocity. The two components of motion, horizontal and vertical, can be characterized separately. This makes modeling complex motion much simpler. With combined knowledge of the law of falling bodies and the law of inertia, we can determine the path of an object's trajectory. We're assuming downward acceleration with some initial horizontal and vertical acceleration to get things started. Let's start this trajectory at the origin of our coordinate system. These equations say that x of 0 and y of 0 are both 0. That centers the starting point at the origin. Here's how we'll express the starting and horizontal velocity. There was some impetus that caused this. Let's also specify an initial vertical velocity. We haven't done that previously. This gives the ball either an upward or downward starting velocity. Upward would be a positive number, downward would be a negative number. We're talking about gravitational acceleration here. We can specify the horizontal position as x of t equals the initial velocity vx0 times the time t. The vertical position is y of t equals vy0 times t. That's the initial vertical velocity. But this time, we subtract 1/2 gt squared. Negative g is the downward acceleration. Here's what that looks like animated. The vectors are all velocity vectors. The graphs are all y component values, since the x component of velocity is constant, which means that the x component of acceleration is 0. The object rises to a zenith point and then falls. The velocity starts out positive and then gradually becomes negative. The point where the y component of velocity is 0 is the zenith point of the object. This is very cleverly illustrated by an experiment at MIT. A golf ball gun is aimed at a monkey who is suspended on a tower with an electromagnet. When the ball is fired, the electromagnet is turned off. At the instant the ball is fired, it will travel in a trajectory, while the monkey will fall. Because they both have the same component of downward acceleration, the ball hits the monkey dead on. Galileo was concerned with the description of motion, not with its causes. That's the essence of kinematics. Central to his formulations was the law of inertia. He sought to describe theories of mechanics, but was never able to. That fell to Isaac Newton. Galileo's law of inertia was Newton's first law of motion. The essential idea was that the motion along a straight line at a constant speed was the natural state of any body. Newton's first law of inertia, in his own words, stated that every body continues in its state of rest or in uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it. He realized that an object's inertia was somehow connected to its mass. The greater the mass of an object, the more difficult it is to prevent it from continuing in motion with a constant velocity. That was the start of Newton's theories of dynamics, the theory of the causes of motion. He developed the second law when he was in his 20s. The first law, what we refer to as the law of inertia, led to Newton's second law. Newton's second law, in his own words, stated that the change of motion of an object is proportional to the force impressed, and is made in the direction of the straight line in which the force is impressed. What Newton meant by motion involved not only a body's velocity, but also its mass. It's the quantity we call momentum, the product of mass and velocity. Stated as an equation, the second law is F equals d dt of m times v, which is the derivative of velocity. Stated as an equation, the second law is F. In situations where mass m is constant, the derivative dmv dt can be expressed as m times dv dt, and dv dt is the derivative of velocity. You'll recall that the instantaneous rate of change of velocity is acceleration. A equals dv dt. Newton's second law tells us that F equals ma, force equals mass times acceleration. Newton never expressed the second law that way. Leonard Euler did 65 years later. It's probably the most useful equation in physics. What is force? In everyday language, it is associated with a push or a pull. When you push on something, you feel yourself exerting a force. When pushed, you feel a force acting on you. Forces originate outside the object whose motion we're considering. In other words, external forces acting on an object can change its motion. The force F need not be a single force acting on a body. It's a vector sum of all the external forces acting on an object. Newton didn't have the math of vectors, but he knew that forces have magnitude and direction. F symbolizes the vector sum of external forces acting on a body. The net acceleration of an object is a result of the total forces acting upon it. We write sigma F to symbolize the vector sum. Newton added one additional law to express what happens when several bodies interact with one another. His third law is, to every action there is always an opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. The essence of the third law is action and reaction. When you push on anything, it pushes back on you with a force equal in magnitude in the opposite direction. The third law is a law of interactions. Mass, length, and time form the basic physical quantities used in mechanics. The unit of mass in the metric system is the kilogram, abbreviated kg. It's equal to 1,000 grams. The gram is the unit of mass in the centimeter gram second system. The unit of mass in the British engineering system is the slug. One slug is equal to 14.6 kilograms. Momentum, being a product of mass and velocity, is a derived physical quantity. In the metric system, the basic unit is a kilogram meter per second. In the British system, momentum comes in units of slug feet per second. Through Newton's second law, force has the same units as mass times acceleration. Therefore, the unit of force is the kilogram meter per second squared, or Newton, abbreviated N. 1 Newton is the force required to accelerate a 1 kilogram mass at 1 meter per second squared. The unit of force in the CGS system is the dyne, and is the force that will accelerate a 1 gram mass at an acceleration of 1 centimeter per second squared. 1 Newton equals 10 to the 5th dynes. In the metric and CGS systems, mass and length and time are all fundamental quantities. Force is a derived unit. In the British system, the standard quantities are force, length, and time. The unit of force in the British system is the pound, abbreviated lb, which is 1 slug foot per second squared. 1 pound equals 4.45 newtons. When an object is in freefall, gravity accelerates it downward with a constant acceleration g. Newton's second law tells us that the force must be F equals mg, where the direction of force is vertically downward toward the center of the Earth. That is what's meant by the weight of an object. Weight is the force of gravity acting on an object, whether it is falling or not. Being a force, weight is a vector. People often confuse mass in kilograms and weight in pounds. These units refer to different physical quantities. Mass is an intrinsic property. Weight depends on location. If you know the mass of an object, you can derive its weight if you know the acceleration of gravity. Moving an object around on the surface of the Earth doesn't change its weight much, but moving it to the moon changes it considerably. Lowering or raising an object where it is in constant motion toward or away from the center of the Earth changes its weight as well. An object in freefall weighs nothing. We typically measure weight with a spring scale. The amount of compression of the spring measures the weight. We typically measure mass with a balance. We put an object on one side and a reference mass on the other until the balance balances. Imagine putting both devices on an elevator. Now imagine the elevator descending. The spring scale will register less weight because the elevator is moving downward. The balance doesn't change, however. The downward motion acts on both sides of the balance equally. Imagine taking the scale to the moon where the gravity is significantly less. If you stand on it, you will compress the spring less. You will register less weight. Like the case of the elevator, the balance isn't affected on the moon. Both sides still balance. Mass doesn't change, weight does. By the way, this is a balance scale. It can measure mass in elevators and on the moon. Galileo was the first to describe the motion of a projectile correctly. Using his laws of inertia and of falling bodies, he showed that projectiles follow parabolic trajectories. He was able to deduce many other properties of their motion. Newton's second law does not change Galileo's description of trajectories, but it puts several separate insights into a unified framework and expresses them in a concise way. One conclusion was that the flight of a projectile is independent of its mass if air resistance is neglected. In Newtonian mechanics starts with F equals ma and uses this to deduce the trajectory of a projectile. We don't know at the outset what the force of gravity is, but we can calculate it from the law of falling bodies. We learned that in a vacuum an object falls with a constant acceleration a, which we can write as a equals minus gk, where k is the unit vector along the z-axis. Since F equals ma, it follows that the gravitational force near the Earth's surface is F equals minus mgk. In Galileo's discussion of projectile motion, the law of falling bodies governed the vertical motion, and the law of inertia governed the horizontal motion. The two laws were unrelated. In Newton's formulation, the first law concerning inertia appears as simply a special case of the second law, applying when no force is present. Since F equals ma, a vector equation that includes three scalar equations in it, includes Galileo's case of a force confined to the vertical direction, with motion in the horizontal direction governed by the law of inertia. How can a single F equals ma equation tell us about the movement of all projectiles? Newton's law F equals ma can be expressed as a differential equation. F equals md squared rdt squared. This is the derivative of the position function r of t. Any function r of t satisfying this equation is a solution to the differential equation. Laws of physics which involve rates of change are expressed as differential equations. F equals minus mgk gives us a whole family of parabolic trajectories,